I'll give you this chair. And
No. Well, you can sit here and I can go over there.
no, that's fine. That's fine.
Oh, that's okay.
Yeah.
Next.
Okay. Thank you. Okay. You ready?
Yes.
Okay, so actually I think basically the way we go, if you get, there are two parts for the proposal. I mean, you two know. And of course you also know. So mostly just Matthias for you.
Oh.
So we have two parts of the proposal. One is this comprehensive exam, the question answers. If you have any specific follow-up on his answers, you get to bring it up here. And of course, the main aspect is the proposal. So unless you would like to do it the other way, I would suggest that we let him do the proposal presentation, and then you can have questions on both the proposal as well as this after that.
Sounds good.
Is that okay?
Okay.
Okay, go ahead.
Thank you. Thank you all for coming here. The topic of my presentation is Foundations of Human-Aware Planning. So I will begin with a brief overview of what human-aware planning involves before we go into the details of the algorithm. So one of the essential capabilities of an autonomous agent is to figure out the answer to the question what to do next. So given what you know of the environment and your own capabilities, you have to figure out what's the best course of action. Now, the problem is that most AI systems are not standalone systems. So if you are deployed in the real world, there will be humans around you, either sharing the same environment or they are interacting directly with the agent. So the answer to the question what to do next cannot be just reasoning over your own capabilities, but you also have to think about how that affects the agents around. And so, unfortunately, most of the work in the planning community has been answering the what to do next question based on the model of the agent, and has not focused directly on how that affects the humans around the agent. So that's the goal of human-aware planning, is to bring in those considerations, how the actions of the agent affects the humans, and how the humans can affect the agent as well. So here's the overall, the classical planning task. So if you're given a model of the agent, and it includes the start state and the goal state, SNG, and given and a set of operators that the agent can perform, and the task is to find the plan, which is a sequence of actions which transforms the start state to the goal state. And so that's the classical planning formulation. However, if you have a human in the loop, you could think of joint plans. So some of those actions in the plan would be contributed by the human, and some of them would be from the agent. And in this kind of setup, you could. So how do you know what the human contributions are? So you have to have an estimation of what the model of the human is. What's the capabilities? What are their goals? And what do they think about the world? So that's the physical model of the human, which says, which gives the robot an idea of if they want to help the human, how to help, or if they want to avoid the human, how to do that. Or they can have coalitions or teams based on their individual capabilities. So MHR here is the robot's estimation of what the human model is. Now, the presence of the human in the loop also means that the robot's actions are perceived differently than what the robot might think by itself. So that brings us to the human mental model, which is an estimation of what the human thinks of the robot. So that's an estimation of the expectations that the human has. So that allows the robot to think of what kind of behaviors are expected of the robot, and also if the robot can anticipate that it's going to do something that's not expected, it can try to explain those behaviors based on those expectations. So that's the MRH, which is a mental model of the robot's capabilities that the human has, and the robot's estimation. And so these two models complete the picture of the human-aware. Yeah.
Sorry, you're talking about models, right?
it's a little too abstract. I mean, are you going to show us what it means to, when you say capabilities, for example, right? Because right now when you say the human's model of the robot's behavior, I'm not
Right,
clear
so that
what I
would
should take
include
from that.
The initial state of the robot, the goals, the capabilities and actions that they can perform.
Sure.
It's everything.
Just the actions or the capabilities?
So, the planning model only has the operators. So it's the operators, initial state and goals.
So you assume that you have the human has the robot's operators in its model of the robot.
An estimation of that. So
Well, yeah, fine. But that's the level of representation,
Yeah, but
right? That makes a difference.
Yeah.
Right.
So we'll get back to that.
Yeah.
So this brings us to the kind of capabilities that you can build on top of these models. So I will go through them one by one. So at the top you have the capability of explanations, which deals with the mental model of the human and the robot's actual model. So in this picture I have denoted the pi star as the optimal plan in each of these models. So pi star MR is the optimal plan in the robot's model, pi star MRH is that in MRH, and pi star MHR is the optimal plan that the human can do. So this is the human's plan, whereas this is the robot's best plan, and this is the human's expectation of the robot's best plan. Now, so the process of explanation comes in when the human's expectation of the robot's best plan is not the same as the robot's best plan. And so the process of explanation is to bring the model, the human's expected model, closer to the actual model so that they are equivalent. So at the end of the explanation process, the human's expected, the human's expected robot best plan is equivalent to the robot's best plan. And this model may still be different from the actual ground truth model, but the explanation process only preserves the fact that this particular plan is explained. You could also think of acting on the actual human physical model, which is the case of serendipity we studied in ILS 2015, where we looked at changing the physical state of the world so as to shape the behavior of the human. So an example of that would be a stigmergic collaboration, where you are changing things in the environment so that the human can find a plan that's better than what they would have by themselves. So here, the resultant plan in the resulting model is better than what the human would have done by themselves. So these two behaviors are in the space of models. So the robot is either acting on the human's mental model or the actual physical model. In the space of plans, you could also think of the classical case of human-robot teaming, where you are finding mutual collaborations. So here, both of the plans have changed to something new that is beneficial to both the agents. In planning with resource conflicts in AMAS 2016, we looked at this idea of how can you preserve what the human is doing. If they're sharing the same environment, how can the robot still do what it wants to do without affecting the human? So here, the robot is compromising from its optimal plan, but ensuring that the human optimal plan remains the same. So the robot's plan changes, but the human's plan remains the same. And in explicability, the task is to generate plans that are closer to the human's expectation. So here, the robot is planning with its own model and the mental model of the robot that the human has, and trying to ensure that the plan is coming up with is closer to what the human expects of it. So this one doesn't involve the human's plan. This one only involves a new plan that the robot has changed from its original plan that's closer to what the human expects in the mental model. So that's an overview of the tasks that I've looked at during my work. The applications of this are in many different applications. So the two applications that I looked at is in human-robot teams. That's on the left, and the particular domain that I looked at is the one of search and rescue. Search and rescue gives us a great test bed for testing out these different kinds of behaviors, because there are multiple agents, some humans, some robots in the same scene, and there's also this idea of an external and an internal agent. So what happens is that there is a usually internal robot that's in the scene, but there is an external agent that's giving it higher level goals. So, so there are also this model differences come in, where the robot is planning its own model, which is also taking into the expectations of the external agent. I've also looked at a bunch of applications in the scope of decision support, and so in different applications like disaster response planning, intelligent tutoring systems, tech support, meeting orchestration, and tour planning. And here the difference between a human-robot team and decision support is that the agent itself doesn't have its own goals. It's only the human has a goal, and they are trying to make the plan. The planning process is for the human, and we are studying what's the role of the automated planner in that planning process. So the roles of the planner are not only creating plans, but you go from validation, critiquing, suggesting, explaining. It's the role of a plan recommender system rather than a planning system. And there also you can study different modes of interaction between the number of agents you have and the expertise of the agent. So, for example, in between expert humans and expert decision support systems, you can have disaster response where there are a fixed set of protocols, but you can have inexpert systems as well, like in tour planning or in the tech support case, where both of them don't have the real model. So either of them are contributing something to each other. So what I will do in this talk is that I will focus on only the explanations and explicability part and show how that argumentation helps in the human-aware planning process. So I will talk about when there is a difference between these two models, how do you explain? And if you know you can explain and be explicable, what's the connection between them? And so most of this work has been published in different conferences. The two papers I will focus on is the ones in red from this year and last year, and the ones in green are part of the proposed work that I will discuss at the end. So this is the setup for the explanations and explicability part. The reason you need explanation and explicability is because when you have the expected model that the human has, if you have an estimation of that, then you can anticipate when there are differences in those models, how your plans will be perceived differently than what you think they are actually doing. So if the robot is optimal in its own model, and the model of the human is different, then the same plan will be inoptimal when evaluated in that model, giving rise to what we call inexplicable plans. So so there are two options to the robot here. So you could sacrifice optimality in your own model and be as close to the expectation as possible, or you can resolve the perceived optimality, suboptimality, by revealing what the model differences are that are contributing to this particular inexplicability. So I will start with a brief demonstration of what this will look like, and then go into the details of the algorithm. So the setup is a mock search and rescue scenario we use on the 5th floor, where there is an internal agent, which is a robot that's going around the scene to different locations, and there's an external agent which has access to the robot's view and can assign goals to the robot. And so the robot gets to complete the task, but also gets to send back the plan that it wants to do in order to complete the task. And this is the map that the external has of the environment. Now, the problem that happens often in these cases is that the map of the world has changed. So both the agents have started with the map of the blueprint of the building, but after the disaster, some things in the environment has changed, which the external doesn't know about. But the internal agent, the robot, is still moving around in this changed environment and has an updated version of the map. So some of the plans that the robot will come up with won't make sense to the external agent. So, for example, if the robot says, I'm going from point A to point B, and that involves an action of going through a wall, then the external agent will think that's not a possible plan. But the wall may have collapsed now, and so that's a possible plan. So this how in this case we end up with two different models.
So here this is not really an operator difference, right?
This is
more
initial state difference.
Right, this is a state difference. I mean, it's an implied operator difference because you can't apply an operator because there's a condition
Yeah, but
missing.
in terms of the model, there is no difference in the
Yeah, so
operators.
right.
There's no difference.
So I guess this
Yeah.
goes back to my initial question,
Right.
which is, it would be nice to have a definition of when you say model, right?
Right.
What you mean by model, right?
So-
I take it that it includes the state,
Uh-huh.
it includes the operator definitions, right?
And the goals.
Right, and the goals.
Yes, and we will come back to an example where you have operator differences as well.
Okay. Okay.
So the difference can be in any one of them. So you can have different expectations. of-
No, I understand. I'm just saying
Yeah.
it would be nice to see it all on one slide
Right.
that says, here is a model, and here are different parts that are being
Uh-huh.
activated in different examples. That's all.
Uh-huh. Yeah, so to be clear, in this case, the difference in the models are only the state. There is no capability. So, so in this case, so this is on the right we have the humans model, on the left we have the robots model, and the optimal plan in the humans model, which is shown in red, is no longer possible because this path is closed. However, the closest plan to that model, to the expected human plan, is the one in blue, which involves clearing rubble, which is a costly action. The best plan in the robots model is not possible in the humans model because there are rubble there. But this rubble no longer exists. So in order to do this, the robot can explain two different changes in the world. Whereas in order to do this, it can do a costlier action and just explain one change that this is no longer possible.
So in that
Yeah.
case, you know that the rubble has been cleared. The robot knows it.
The robot knows it.
And
yes.
the robot also knows that the human does not know it.
Yeah, because this was the
Right.
yeah, this was
So what about cases where the robot does not know that the human doesn't know it?
Right, so then you have to iterate on that. So if you provide an explanation, so there are two cases, right? So one is your model is older, so you are providing information that the robot or the human already knows.
But or
So
maybe
it's up to you.
it's different to begin with. Right?
Right,
It doesn't have to be older. I mean, you
Yeah,
just
so there are two cases. One, so if it's older, then you're providing information that's already known. The other case, the human needs to come back and say that this is not right.
no. All right, but maybe we should take that afterwards. But I'm thinking of cases where they actually have to find out that they're talking about two different things, right?
Uh-huh.
That's different. Let's bracket that. Let's get back to that.
Okay,
after.
sure. Okay, so yeah, I will describe how this is actually performed, but I will just play the demo first. Yeah. So this is the scenario. This is where the rubble removal scene was.
The user gets the video feed only.
Right at the top.
Do they get to see the map as well?
And this one.
This one.
And so, in their case, the robot is taking this path, and the older path after the update is blocked. And so this involves the explicable plan, because they have to do the costly action. So the next example would be about the one with the explanations, where these two locations, which are blocked in the humans model, the robot gets to come back and say that these are no longer blocked, and that includes two explanations which will appear at the top. So this is the next example. Yeah, so the top panel includes the explanations communicated from the robot, and it's saying which paths are now clear, and takes the shortest path that it can do. All right, so the first option that we talked about is this idea of explicable plans. If you want to conform to the human's expectation, you produce plans that are closer to that. So the way this was done in was to compute a similarity function between what you think, how similar you think your plan is, close to the actual explicable plan. So you can use that similarity function in the search process, so as a heuristic. So then one of the problems in explicability is that if you have an estimate of the human model that requires a plan that's not feasible, then you can't just use that model to produce a plan, because the human's expectation might not be feasible. So then you can't just use that model directly, but use the similarity function is a heuristic to guide the search towards plans that are more explicable. So that's the general idea. But of course, given that those plans, the most explicable plan that the robot produces, may not still be the one that the human expects, you may still have to explain. Okay? So you have to explain why your plan differs from the expected one. And the key idea here is that this explanation cannot be a soliloquy. So the robot cannot be talking about its own model during this explanation, because it has an estimation of the human model and it knows the root cause why its action is not explained. And so the explanation should be done in terms of its own model versus what's different in the expected model. And so the setup is this. So the robot comes up with a plan that is optimal. And the explanation is a model update to the human, which makes sure that the plan is optimal after that. So in the picture, the expected model is here, produces this plan. We produce a model update, which we call the model reconciliation process. And after the model reconciliation process, you have a new model, which both the agents agree on, where these plans are given. So let's look at an example, a historical example that we had in the lab. So this is in the fetch robot again. And so the fetch robot, when it needs to move, it needs to tuck its arm and lower its pace before moving. But for a general mobile robot, the move action is just move from point A to B. And then there's a tuck action which does the hand tucking, there's a crouch action. So if you as a human is telling the robot that move from point A to B, it would include this action in the middle, which of course would seem like, well, this is extra, you don't need to do this. Right? So if we ask, why do we need to do this extra action? Then the robot has to come back and explain parts of its model, which are typical to its own model, and say which of those contribute to making this plan the best that it could. So the process of explanations here is to figure out what is this update, right? To compute which parts of this domain it should externalize. So yeah, in the scope of those different kinds of explanations that we can give, we looked at different properties of an explanation and how you can get different kinds of explanations the model of this out. So the simplest kind of explanation is an MP, which is the model patch explanation. So you give all the updates. So whatever the difference in the model is, just give those. And so the point is that that's very easy to compute. If you have an estimation, you just compute the difference, give that. And it also ensures that the optimality property is preserved because they have the same model at the end. However, it can be arbitrarily picked. So it's a very simple example, but in the scope of general interactions, there may be a huge number of differences which are not relevant to this action at all. So MPs can be quite big. The next one we looked at is PP, which is plan patch explanations. The point of a plan patch explanation is to only look at the actions in the plan and provide explanations for those actions only. So differences in the model that are corresponding to actions in the plan only, nothing else in the domain. So actions that have not been performed do not appear, only the differences relevant to those actions. This means that you are ensuring that this plan will be feasible after the update, but there is no guarantee that this plan will be optimal. And the reason we need the optimality is that we want to make sure that not only we are explaining this plan, but we are also making sure that it's better than other alternatives that are possible. So if there are other foils that the human asks, like why not this other plan? By ensuring that after the update we are optimal, we are ensuring that the optimality property holds. So PPs are also quite easy to compute, but they do not have the property of completeness or optimality. And in this case, in the worst case, they are as big as the NP. So in this case also, it's as big as the NP. Now the interesting case of MC is the shortest the possible explanation that you can compute. that preserves the optimality condition. So these are the shortest the smallest set of model changes that will ensure that condition. So in this case, that change is shown in blue. And out of the 3 changes, if you just say that the precondition is crouched, then this model will ensure that this model is optimal.
So is that because crouched has as a precondition that hand be tucked?
So in the human's model,
No. Right. Can the human infer that
Right.
if crouch is there, the hand must be tucked?
correct. So because you have to do that in order to, because the hand tuck is already there in the platform. So you could either say,
Oh, because that's there, but suppose it weren't.
and then you have to give both. So in this case, you could say hand tuck is a MC as well. So if you say hand tuck is a precondition,
Yeah, so it is not a precondition for crouch in the human's model, but if it were,
right?
then if you just give crouch, right, and you assume that the human has a particular reasoning capability,
Right. So the human's reasoning capability that we assume is that after that update, they are producing this plan as optimal. So even if you do not provide crouched as a effect of tuck,
so, okay, but pre and post conditions may be
Right.
connected via inference processes.
Right. yeah, but so
You don't do that.
We don't see what the second order reasoning is.
There's no second order, it's still first order, but it's to
We
see
do-
that a post condition, for example, of anywhere in the plan, if you arrive at a state, right, to then determine whether another operator is applicable, you need to satisfy the preconditions, except the preconditions may not be in your set of states right now, but they may follow from that using some inference system. See what I'm saying?
Right.
And you're not doing that here.
Right.
But so, okay, good. So,
yeah, so we are only so
you have to actually find that pattern directly.
Right. So
Okay.
the robot says directly that this is there.
Yeah, it's fine.
And so
And also, one thing that would be nice is kind of an actual definition of explanation. I'm a little bit unsure exactly what an explanation is in.
Right.
That's right. Explain what an explanation is.
yeah, so the definition of explanation is this. So the human aware planning problem includes the model of the robot and the model of the human, the estimated model of the human. So that includes the state, goal, operators, everything. Model of the planning problem. Now, if the solution to the human aware planning problem, if that's an optimal in the robot's model, then it may or may not be optimal in the human's model. So the explanation problem is to give an update to the human's model. So the explanation is the model update, whereby after the update, both the models agree that this is the optimal plan. So the human model here may not be the same as the robot model, but in that model, this plan is equivalent to the optimal plan you can have here. So you can't do better than that. So is that?
No, I think you're again giving the process. I think just an explanation. What's it?
The
What is
explanation is
an
the
explanation?
Explanation is the model update.
Exactly. Say that.
Yeah, I think the question is more, and we can do that later, but the question is more, is that really an explanation? Because there's the assumption that we know actually what is going on, kind of our estimated model of
You don't
human's
have to know
plan.
exactly, yeah. But
So
I have an estimate of what it is.
I think if you talk to the philosophers,
Uh-huh.
right, they would say that this is the result of an explanation, the model
Yeah.
update, but it's
Yeah.
not the explanation.
Itself, yeah.
Right.
I'm sorry, I didn't get what you
Yeah.
said. What do you mean?
The model update, it can or cannot be the, depending on whether you believe the explanation or whether you find it intuitive, can be the result of the explanation, right? The explanation is something that you tell the other person, which has the effect of updating your model.
Yeah, but I mean, so then you are.
So you assume, so the point is here,
right?
here you're assuming there's no communication issue, there's no way of, right? You just basically implant into the other person's head immediately the propositions that they need to update, right? And you're not worried about it. That's what I think what he was getting at. And that's what
So-
typically,
The-
So if the human thinks that there's a wall there and the robot knows there's no wall there, what if the robot just goes through the imaginary wall anyway?
Right.
Would that be a way of explaining to the human that there's no wall there?
So that's a
Yeah.
case where you don't have to, we will come back to that point later. Yeah, so that's a case where you don't have to explain.
Where you build on the human inferential capability to then notice that the model was wrong and then they update. So for you, it would not make a difference, right? But that would not be an explanation. This would just be the human noticing that they had a wrong model.
Right. But then you have to have a model of how the human updates the model there.
Oh yeah, you do it for the robot side, right?
Right.
But irrespective of the robot's model, the human would just
Right.
do it, right? Wouldn't need an explanation.
Mm.
You would just see it.
Right.
Anyway, I think it's second. I mean, it's a separate thing because they use the explanation in a very clearly technical sense here.
Yeah.
But just be aware that a lot of people would not call that an explanation because the explanation intrinsically involves the communicative aspect
Yes.
of giving you a sequence of statements that relate in a way that then allows you to perform the model update. Whereas you just, right, you give me the propositions that I need to take and fix in my model.
Right.
And that's okay.
Okay. Yeah, and so we are at MCs. So the point of MCs is that they might not be unique. So there are many different MCs. And a problem with MCs is that with further explanations, previous explanations might become invalid. So, for example, in this case, if the human found out that the crouched precondition also exists in duck,
Yeah.
then there might be plans later on where this explanation is no longer a valid explanation. So we looked at this idea of monotonic explanations, where you want to ensure that, irrespective of further model updates, the previous explanation remains always valid for that particular plan. So that's the minimally monotonic explanation, and it may or may not be a superset of MC because neither one of them are unique, but it's usually bigger than the MC.
So why is that complete?
So MCs are always complete. So you are ensuring two different conditions here. One is that the optimality condition holds, and as with more of model updates, that will never break. Whereas in MC, it's just that the optimality condition holds. So the way we find those explanations is what we call model space search. The process of model space search is to figure out an intermediate model where the optimality condition will hold. So in the case of MCs, you start from the expected human model, make unit model updates to that, and all these model updates are consistent with the robot's ground. So in every step, it's bringing the human model closer and closer to the actual ground, and checking where the